Well, hello, class. We are starting chapter 2, looking at chemistry. So this is the first of the videos. So let's see what we've got going on. So I do get this pretty often. Students will ask, why do we study chemistry? Most students do not like the chemistry aspect, but you've got to understand that um, the name anatomy and physiology. Physiology is the study of how things work, and when you're talking about the body, it's pretty much all chemistry. So you have to have chemistry. I'm actually going to take my screen off there. Um, so chemistry is concerned with the composition of the substances and how they change in chemical reactions. Our body is, like I said before, we are basically a walking chemical laboratory. And so we've got all kinds of things going on. That's where the word metabolism come from, is all of the energy and the reactions that are building up and breaking down as, in total, we look at that. And it's all chemistry. So chemistry is the study of matter. It's chemistry is the study of matter as it pertains to it, and then matter is anything that takes up space and has mass. It needs both of those. I always say in my class, I try to point out there is one thing that we are constantly around that does not have mass, um, and so it is not considered matter, but pretty much everything that we come in contact with or can think about is matter. The one thing is light. Light is a massless particle. And so it's kind of weird, but anyway, matter is anything that takes up space and has mass. And mass is a measurement of how much matter is present, and that is different than weight. We kind of use them interchangeably here because, see, what weight is the heaviness of that matter due to gravity. And so when we are looking at it, our mass will stay the same no matter where we are, but our weight might change depending on if we're on the surface of the earth or the moon. And so while we use them kind of interchangeably here, true definitions have them separate. So, and then chemistry is the study of all of this. So biochemistry is the study of the chemistry of life processes, the biological chemistry. And so anyway, this is just giving you a couple of definitions. The two real important definitions is matter and chemistry, but I hope you understand the difference between mass and weight as well. Now, this is a picture of the periodic table of elements. From what we can see of our entire universe, everything, it is broken down into elements, right? And this is an organized chart of them. And we'll come back to this and kind of talk about it. This is the way we would look at it in isolation, each one of these. And each one is considered an atom, or an atom is the building block or the fundamental particle of each one of these elements. So elements, the simplest type of matter with a certain chemical property, and we'll see what that is in just a minute. It is actually the number of electrons, which we'll see is tied with the number of protons and whatever. Compounds are when these elements combine. So atoms are the smallest particle of any element. And so when atoms of different, atoms combine, we can call those compounds. Or molecules. So anyway, it's got to be different elements to be a compound. So anyway, there are certain elements that we need a lot of. There are 4 that we can really consider bulk elements. This has 6 listed, but we'll just briefly look at those in a second. Then we're going to have a good amount of trace elements that we just need a little bit of. And then there's ultra trace elements, which we need very little of. So when we look at the atom, so the atom's the smallest particle of an element that has the properties of that element. This is when we looked at that little building chart. Subatomic particles make atoms, atoms make molecules. So the atom, again, the smallest part. And so this atom is made up of neutrons, electrons, and protons. Now, when we look at these elements, again, which the atom's the smallest part of, we said that there were some that were called bulk elements. And so really the first three are the main bulk elements. Now you have nitrogen and you have calcium in there, but really the first three are the big ones. And that is because first, water, H2O, makes up the majority of our water, so our body. So obviously, hydrogen and oxygen are going to be two of the bulk elements. And then all of the organic molecules, those macromolecules we mentioned again on that building chart, all of the organic molecules use carbon as the chain. And we're going to see that by definition, something that is an organic molecule is going to have carbon and hydrogen. So this is why they are considered the three main bulk elements, because all of our body is made up of mainly organic compounds, particularly proteins. And those, the building blocks, the majority of it is carbon. It's going to have hydrogen on it. And since water, H2O, is the other thing, that actually the most abundant thing, it makes sense that the three main bulk elements are oxygen, carbon, and hydrogen. Now, atoms are going to be made up, like I said, of three subatomic particles: protons, which carry a positive charge; neutrons, which are neutral, right? They have no charge; and then electrons, which have a negative charge. Right? So this is like the equivalent of like a magnet. If you've ever seen, a lot of times you can have a magnet and it'll have a positive pole and a negative pole. And so the way that atoms are set up, you've got a positive particle and you've got a negative particle, and the third particle has no charge. So atoms consist of a central nucleus, which is made up of protons and neutrons, and electrons in constant motion around the nucleus. We commonly look at it, we'll see a drawing here in a minute, where you got, protons and neutrons here in the nucleus, and then electrons are moving around in what we'll call little electron shells around the outside. So the number of protons equals the number of electrons in an atom in a idealized world. Now we're going to see that the electrons are going to come and go if needed, because we have a basic model of what makes an atom happy. So in an ideal world, you have the same number of protons as you have electrons. All right. Now I say this in class. I'll tell you, it's kind of like the difference of having a family that sends you a Christmas card, and both the parents are all dressed up and they're smiling, and their kids are all nice and dressed and they're smiling. It looks like everybody gets along, but you know that family and they're a mess. The kids are always fighting. The parents look disheveled all the time or whatever. And you look at it, and so there's two views. There's the Christmas card view of the, oh, how nice. And then the real world view of like, oh, okay, now I see. Well, this part right here is talking about the Christmas card view, what the idea of it would be. So when we look at the structure, again, like I said, you've got a nucleus that consists of the protons and the neutrons. And then around the outside, you're going to have electrons that will kind of move around. And we call them orbits. Now, if you've taken physics, or if you are going to, you'll find out that this is much more complicated. There's this little circle. They call them clouds, actually. But for us, they're called orbits. We'll look at them just in the simplest view. Now, this is really important to understand. And again, when we go up to it, we have, you've got an electron, you've got a proton, and you've got a neutron, right? Electrons are negative, protons are positive. This is neither. So, right? Now, these two are in the nucleus. This one is flying around in the outer shell. So when we look at these, the atomic number is a very important thing. This is simply the number of protons. right? So if we went back to that periodic table of elements, it is organized by atomic number. Now, if I know the number of protons, I know the number of electrons in that Christmas card, all right, in that view of the what it would be in an ideal world. So if I know the number of protons, I know the number of electrons. So the atomic number is the number of protons. And if I know the number of protons, then I can carry it forward and know the number of electrons. Does that make sense? Now, the next number we have is the mass number. Sometimes we refer to as atomic weight because, again, we kind of misuse the idea of weight. But a lot of times it's called the atomic mass or the mass number. So they're all kind of saying the same thing. And so what we're looking at there is, see, electrons have absolutely minute weight. As a matter of fact, they're considered, borderline as a massless particle because they have no weight. But in this, we kind of consider them massless because we don't count it. So the mass number is the number of protons plus the number of neutrons, because these are the only two particles that have any real mass. So electrons don't contribute. So if I know the number of protons, I know the atomic number. So let's say the atomic number of an element is 9. I automatically know I have 9 protons for sure. In an ideal world, I would know I have 9 electrons. We'll see how it changes in the real world. But let's say I have a mass number now of 18. Since the mass number is the protons plus the neutrons, I know I have 9 protons. If I want to find the number of neutrons, I just subtract 9 from 18 because whatever is left over is telling me that is what's here. So if I have an element that has an atomic number of 9 and a mass number of 18, I know then it has 9 protons and 9 electrons, right? So, or neutrons, I should say. Sorry about that. And in an ideal world, it would also have 9 electrons. So I hope that makes sense. So if I had the mass number as 20, you would know that there would be 11 neutrons because, again, we know that 9 are the protons. I hope that makes sense. Now, isotopes, we're not going to spend a lot of time about isotopes. The only thing I want you to know about isotopes is that we're talking about elements. So they all have the same atomic number. They have the same atomic number. So let's say I go back to the one that had the atomic number of 9, which is saying that I have 9 protons, right? I'm just going to write pro here because, I'm using the little keypad and it's frustrating. So these are the protons, right? We know they're positive. In an ideal world, we know that we have 9 electrons. Also, electrons, we'll say and we know that that is negative particles. In an ideal world, we'll see in just a minute how that would work in the real world. So I've got an atomic number of 9. Now, if I said, just like we were talking about the mass, the atomic mass, or the mass number, and I said that the mass number is 18, that's saying, since I know I have 9 protons, that means I have 9 neutrons, right? I hope everybody kind of sees that. I hope everybody can do that math. Now, I can have the same element, again, same atomic number, but end up having different, mass numbers or atomic mass. So let's say if I have one that has an 18, I have one that has 19. So I know that this atom now has 10 neutrons. So I have 2 different mass numbers. And it's because I've gained or lost a neutron. Anytime I gain or lose a neutron, this is referred to as an isotope. Now again, isotopes are going to be things that have the same atomic number but different mass numbers. And so this is where this ends up being this can be radioactive and unstable. If you're going into rad tech, you'll kind of get into this a little bit. But to me, the only thing I want you to know is isotopes are all about the gaining or losing of neutrons, all right? Because for us, really the main thing we're going to look at is electrons, which is how these interact. So isotopes are kind of special. Remember, isotopes are all about same element having different numbers of neutrons, so they would have a different atomic mass or mass number.